Hi, my name is Carissa Garrity. I'm a fifth-year PhD candidate at the University of California, Davis in the PMI department under Dr. Natalia Bapanarski's laboratory. And I will be presenting on my research, tissue engineering of immune universal cartilage. The cartilage is a viscoelastic tissue that lines the ends of diarthrodial joints. Cartilage has a poor regenerative capacity, and once degradation has occurred, the tissue continuously degenerates. This can lead to debilitating and painful conditions. Tissue engineering offers a potential solution to replace the tissue that has been lost. Tissue engineering is the combination of cells, scaffolds, and stimuli to construct tissue. But before you start tissue engineering, you need to determine where you're going to source your cells. The most efficient cell source to use are allogeneic chondrocytes, or cartilage cells derived from a donor, due to its ability to harvest from many donors ahead of time and create off-the-shelf, ready-to-go implants. However, the risk of allogeneic cells is a potential immune rejection and disease transmission. The molecule primarily responsible for immune rejection is the major histocompatibility complex, or MHC1. This molecule is on the surface of all nucleated cells and is highly polygenic and polymorphic. But by targeting beta-2M, a conserved structural component of MHC1, we can knock out MHC1 across many different individuals easily. No group has yet to try this knockout with chondrocytes and investigated its effects on chondrogenesis. Therefore, my project is split up into three main aims. 1. Design and develop beta-2M knockout in coastal chondrocytes using the CRISPR-Cas9 system. 2. Validate the knockout efficacy with flow cytometry, qPCR, ELISA, and lymphocyte chondrocyte co-cultures. And 3. Tissue engineer cartilage tissue from the knockout chondrocytes. After confirming the knockout with Sanger sequencing, we performed the following experiments. We validated the disruption of MHC1 and beta-2M expression with ELISA, qPCR, and flow cytometry. We saw a decrease in MHC1 expression in the knockout in comparison to the wild type. This was further confirmed with multiple biological and technical replicates in the graph in the center. We also confirmed at the genomic and cDNA level with qPCR. We saw a significant decrease in cDNA expression level of beta-2M in our knockout versus our wild type. While all these results show that beta-2M and MHC1 expression is downregulated with the knockout, it doesn't prove the knockout is functional. Are these chondrocytes actually invisible to the immune system? This leads me to the next validation step that we did, which was to perform a co-culture. We plated our wild-type and knockout chondrocytes with allogeneic PBMCs and measured the PBMC proliferation. We saw a significant decrease in PBMC proliferation when co-cultured with knockout chondrocytes in comparison to our wild-type. Finally, we tissue engineered cartilage constructs from our wild-type and knockout chondrocytes. Future directions would like to explore the proliferation of different lymphocyte subsets within our co-cultures, such as NK cells and CD8 T cells. And finally, we would like to try this knockout in other species and cell types. Thank you.